Hello, everyone. Before diving into today's topic, we want to take a moment to thank you for your support. Every like, comment, and subscription truly makes a difference and helps this channel grow. If you enjoy our content and don't want to miss our upcoming videos, subscribe to the channel and activate the notification bell to receive all updates. The Möbius strip is one of the most fascinating surfaces in mathematics, with applications ranging from topology to physics, from art to technology. Discovered independently in 1858 by German mathematicians August Ferdinand Möbius and Johann Benedict Listing, this object has the peculiar property of having only one surface and one edge, a characteristic that makes it unique and has inspired numerous studies and practical applications over the decades. Constructing a Möbius strip is simple and intuitive. Take a rectangular strip of paper, twist one end by 180 degrees, and join the two short sides together. The result is a surface with surprising and non-intuitive properties. If you try to trace the surface with a pencil without lifting it, you will notice that you traverse every part of the strip without ever encountering an edge, demonstrating that the surface is unified and lacks a separate inside and outside. From a topological perspective, the Möbius strip is a classic example of a non-orientable surface. This means that there is no consistent way to define up and down across its entire surface. This distinguishes it from orientable surfaces, such as a cylinder or a sphere, where it is always possible to establish a unique and consistent orientation. Non-orientable surfaces play a crucial role in mathematics and theoretical physics, especially in string theory and cosmology, where complex and non-intuitive topologies are studied. Another interesting feature appears when attempting to cut the strip along its median line. Instead of obtaining two separate strips, as one might intuitively expect, a single longer strip is produced, this time with two twists. If this new strip is cut again along its median, the result is even more surprising. Two interlinked rings are formed, a phenomenon with significant implications in topology and knot theory. This counterintuitive behavior has led to extensive research in both pure and applied mathematics, inspiring studies on interwoven structures and alternative geometries. Beyond being a mathematical object of study, the Möbius strip has found practical applications in various fields. Physics and engineering. In electronics, some transmission bands use Möbius strip-based configurations to improve signal distribution and reduce interference. Additionally, in optics and printed circuit design, the concept of a non-orientable surface is applied to optimize signal pathways. In mechanical systems, certain configurations exploit this structure to create components with greater efficiency and resistance to wear. Chain conveyor belts. Some industrial conveyor belts are designed with this geometry to distribute wear evenly across the entire surface, increasing their lifespan and efficiency. A Möbius strip allows both sides to be utilized without needing to flip the structure, reducing long-term deterioration. Art and design. The Möbius strip has inspired numerous artworks such as those by M.C. Escher, renowned for his explorations of impossible geometries and optical illusions. In architecture, some structures are inspired by this form to create unique visual and spatial effects. Möbius strip-based sculptures can be found in various cities worldwide, symbolizing infinity and continuity. Chemistry and biology. Certain molecular structures exhibit characteristics similar to the Möbius strip, such as some aromatic compounds known for their unique stability. In molecular biology, some proteins and DNA structures can adopt analogous configurations, impacting their function and stability. The topology of the Möbius strip is also applied in superconductivity research and nanotechnology, where surface geometry plays a crucial role in conductivity and material resistance. The influence of the Möbius strip extends to literature, cinema, and philosophy. It is often used as a symbol of paradox and infinity. In the film Inception, for example, some architectural concepts echo the topology of the Möbius strip, creating spatial illusions that challenge the perception of reality. In philosophy, it is used to illustrate continuity and the interconnection between seemingly separate opposites, such as the duality between subject and object, reality and imagination. In literature, the Möbius strip is frequently used as a metaphor for cyclicality and eternal return, a theme cherished by many philosophical movements. A particularly fascinating aspect of the Möbius strip is its use in dynamic systems theory and applied mathematics. It is studied in relation to chaotic systems and mathematical models that describe complex natural phenomena, such as fluid flow patterns or magnetic field configurations. Additionally, its structure has been utilized to develop algorithms and computational methods in various fields of data science and artificial intelligence. The Möbius strip remains a source of wonder and applications across numerous domains of human knowledge. Although simple in its construction, its mathematical significance and implications make it an object of great interest to scientists, artists, and philosophers. Studying and understanding this surface means exploring a world of paradoxes and hidden symmetries, revealing new perspectives on the nature of reality and the connections between seemingly unrelated disciplines. Its continued presence in research and culture demonstrates how a mathematical concept can profoundly influence how we understand and interact with the world around us. Its implications continue to expand, suggesting that its potential remains largely unexplored. Thank you for watching. Subscribe to the channel to avoid missing upcoming videos.